Hari Om and good afternoon, everyone. Welcome back to day 3 of ICRACM 2024. Let me take this opportunity to welcome the session manager for this session, Ms. Nibi Babu, Assistant Professor in the Department of Computer Science at the CVV Institute of Science and Technology. Also, this will be the last keynote address of this session. Ma'am, please.
Good afternoon, everyone. It's my immense pleasure and honor to welcome all of you to the last keynote section of the 7th International Conference on Recent Advances in Composite Material, organized by Chinmay Vishwavidyapith, deemed to be university. We are delighted to welcome such a passionate and diverse group of participants gathered here to explore and discuss the most recent advancements in composite materials. To ensure a seamless experience during the section, we kindly request your cooperation with the following guidelines. Please ensure your microphone remains muted throughout the presentation to avoid any disruptions. We encourage you to actively listen to the sections. If you have any queries during the presentation, please type your questions in the chat box and the speaker will address them during the Q&A section. Let us all maintain professional decorum by refraining from interrupting the speaker during their talk. Thank you for your attention and cooperation. We look forward to an inspiring and thoughtful section ahead. Now, it's my privilege to welcome our esteemed keynote speaker, Dr. Negeshwara Rao, who will be presenting on the topic Fracture Strength of Composites to Ensure Structural Integrity and Safety. Dr. Negeshwara Rao earned his MSc in 1975 and his PhD in 1982, both in mathematics from IIT Bombay. He dedicated 33 years of his role as a scientist engineer at ISRO VSC in Trivandrum from 1979 to 2012. Since 2012, he has been serving as a professor at Koniro Lashmaya Education Foundation in India. He has received several honors, including the NCCC certificates, the IIT Bombay Merit Scholarship during his postgraduate studies, and the prestigious Junior Research Fellowship from the Indian government's Department of Atomic Energy, as well as a Senior Research Fellowship from the Council of Scientific and Industrial Research to pursue research for his PhD at IIT Bombay. He has authored or co-authored 436 journal articles and contributed 51 articles to various conferences. His research contributions to scientific journals and conferences encompasses a range of topics, including MHD, non-Newtonian boundary layer flows, performance analysis of coal-fired boilers in thermal power plants, CFD simulations validated with test data for heat exchangers, waste heat recovery in process industries, optimization in manufacturing using a modified Taguchi approach, development of hybrid finite elements, creation of specialized elements for bonded joints, rigid body dynamics for separating bodies in space launch vehicles, superplastic forming and hydroforming forming in deep drying process, among others. He has effectively supervised 23 PhD and many BTech and MTech projects. He has held the positions of research guide at both the University of Kerala and Andhra University. He is a member of various national and international professional forums. Furthermore, he has delivered lectures and provided guidance of project thesis for participants in the ISRO induction training program and has presented keynote address at both the national and international conferences. He has been recognized as one of the top 2% of scientists globally for the years 2020 to 2024 as announced by Elsevier in collaboration with Stanford University. Let us extend a warm welcome to Dr. Negeshwara Rao to share his insights on fracture strength of composites to ensure structural integrity and safety. Over to you, Professor.
Okay. Unmute చేశారా? Yeah. Thank you, madam, for your introduction. Am I audible?
Yes, sir,
Yeah.
you are audible.
Yeah. Yeah, let me thank the organizers for giving me an opportunity to share some of my thoughts related to fracture strength of composites, and the participants also. I am thankful to them to hear their valuable suggestions after my lecture. So the fracture strength of composites, it is essential to ensure the structural integrity and the safety of the systems. As you know, composites world, when you look into the Google search, they are releasing several magazines every day. Some new thoughts are coming related to composite structures and manufacturing and material making and their things. Nowadays, even some of the waste material also they are converting to composites, and they wanted to make use of it. So when you look into it, broad prospectus is there related to composites materials. It is not only the development of the material, we should utilize the full strength of the material. So when we go for advanced thing, when individual component wise the design is adequate, the moment when you are joining the components, their performance, their life expectancy through non-destructive testing is a challenging task. We need the expert system to identify the defects, if any, during the service, and if we get it, identify the particular component, it can be replaced or repaired and use it without failure. So till then, this type of fracture strength evaluation for any material is demanding. So now my presentation here concentrates the moment of strength. When you say the failure of any component, prior to failure, damage will be introduced in your body. So whatever damage, what type of damage, it is realistic or unrealistic or artificially created damage, to study the impact of the damage on its life of the component. So what is the residual strength of composite materials after impact? Impact loading, when it is happening, suddenly applied load, the structure will be getting damaged. So what is the load bearing capacity? Whether the non-destructive testing will assess the damage, and the structural expert system should predict its life. It is more important. So unless we study its behavior on a sample level, we cannot translate that knowledge to the actual product. Second one, damage assessment in composites through AE monitoring. Suppose when we are trying to, after impact, we will not be knowing internally how much damage it has taken place. Suppose a small amount of load if you apply through acoustic emitter monitoring, we will be in a position to find out the residual life of it. It is a wonderful idea. Some of the latest literature also it is showed promising. Though acoustic emission monitoring is frequently being used in the pressure vessel technology, in composites, because of its complex nature, failure nature, it is also helpful in identifying the residual life of the body. The another one is bond strength. The bond strength of a simple lap joint, single lap joint, configuration should be simple, so that we can understand the mechanism of failure, so that we can extend that mechanism to a complex joint configurations. It will be beneficial. That's why I have selected this topic to present you. The fourth one is failure pressure estimates of composite overwrap pressure vessels. It is a highly demanding. Every day it is changing a lot of design philosophies. So now this is the fifth type of the composite overwrapped pressure vessel people are demanding. Metal lined and linerless. Many things when you look into the literature, the designers are struggling to design the component which will be useful without leak. So another one is the failure pressure estimate, because all these components requires the failure assessment. Otherwise, we will not estimate its safety. But these are all the things not theory based. Experiment is supporting. Then based on that small scale level, if you can translate that knowledge to the full scale, then we will be beneficial. That's why I have selected these few problems. If I can explain and make you understand how we are trying to interpret from sample level to the actual product. So now, when you look into the mechanical engineering stream, any structure failure, there are many categories. So brittle fracture, fatigue, yielding due to overload of the cross section, leakage of containment vessels, corrosion, erosion, fatigue, stress corrosion, instability, creep, or fatigue interaction. Some of them, when you talk about yielding, it may not be directly applicable to the composite materials, because it is no yielding taking place unless the metal matrix composite or somewhere else. But majority of the things, it will be a linear breaking. Next. Then when you talk, since I have spent a lot of time in ISRO, space research, we are mainly focusing on failure criteria, either yielding or fracture. So generally, no component will allow beyond yield. Whenever we apply load, it should be below yield. But when you estimate the safety factor, we have to assess, we have to load beyond yield and see its failure. Then only you can understand what is the residual life of the component after applying a load. The fraction, both are failure things only, why it had to be differentiated to. After yield, there is ultimate. So in metallic cases, purely ductile materials, it had to yield, then the yielding will progress and approaching to the ultimate. In case of composites, directly breaking. Fracture. Fracture means yielding and breaking also damage had to create and fail. Here fracture means because of the crack-like defects, it will be failing lower than the design load. So these two things are important when you talk about failure criteria in rocket industry. But majority of the failures, experimentation with variety of materials, so that the theory works well for certain materials, but not very well for others. That means it is the experimental evidence is cautioning us. No universal theory is applied for all the materials. When metallic itself, this type of thing is there, the multi-directional strength variations are there in composites. You cannot imagine. So the designer had to use or establish a suitable failure theory for the intended materials. Whichever new material you are taking, whichever new material we are going to use, or new product we are making, we have to carefully examine at the lab scale level, try to understand the failure behavior, then implement those thoughts in actual hardware. Then only we will be in safer side. So one is yielding, another one is fracture. Yielding means some function of the stress should not exceed the yield strength of the material. Still there is remaining life up to ultimate. Whereas fracture mechanics, it suggests you have to measure experimentally the fracture resistance, means that is called fracture toughness, under monotonic as well as cyclic loading. Then only you can assess the structural integrity utilizing the measured data. So majority of the people agree the extraordinary success of fracture mechanics lies in its ability to combine theoretical framework with the experimentally measured critical quantities. Then only you can say the life expectancy is reasonable. General fracture processes in composite materials are complex because the properties are varying in the directional way. The strength properties also will vary, and there are many theories are available that we will be discussing briefly, so that one of the theory may work, or you may have to develop your own theory for the material. When you look back to the history in 1960 itself, the strength-based criteria, the design of pressure vessels during proof pressure testing itself, unexpectedly they failed. When they examined the failed surface, they noticed a hairline cracks that has created premature failure of the components. It made them to open their eyes. There are a sharp cracks that the tip has got concentration much higher. So it has created further growth and reached to its critical stage and failed. So the fracture mechanics started from 1960 onwards in aerospace industry and in petrochemical plants. So when you look into the boiler safety accidents, this is a storage tank, a spherical tank. They were resting on a support legs. Unfortunately, what happened? A water is trapped between the insulation and the support.
Professor, are you able to hear me?
Yeah.
Sir, the slides are not changing.
Now, madam?
Now is it okay?
The presentation slides are not changing, sir.
Yes, it is not in the full screen mode, so it is not changing.
Okay. Sorry.
Sir, now it's okay? No. We cannot, the slides are not moving. 1 minute, sir.
Sorry, sir. Continue, sir. Sorry for the disturbance.
No problem. Please tell me whether it is moving or not.
Madam, now it's okay? Hello? Now it is not in the full screen mode.
Yeah, now you please see.
Sir, now it's full screen mode? No. Sir, now it's okay? You put it in the full screen mode, please. Now? Yeah, go ahead.
So now, when you talk about boiler safety accident and all, this is one gas storage spherical tanks. They were supported by the support legs have corroded due to water trapment between insulation and support column. It is collapsed. The worker killed. Many such things are happening. So one should be very careful in each and every failure aspect of it and the safety aspect of it. So the another one, it is a brittle fracture. How it is caused? The structure was designed with room temperature water, but it was loaded with cool water. So as you know, when it is in a room temperature, below room temperature thing, the material will become brittle and initiate the cracks. It is not that just because of the load, because of the environmental effect, the strength is degraded. When you are applying some small amount of load pressure, it is created the fracture and failed. The other one is because why this essential, When you go for the metal-lined pressure vessels, we require the failure behavior of metal as well as the composites. So now, when you talk about a small change in the chemical composition, the failure behavior is changed. You see the left-hand side 15 CDV6 steel, it is able to take till ultimate tensile strength of the material. Whereas electroslag refined to improve the strength of it, it is able to take up to yield strength of the material. That is the reason why the aerospace industry is interested not to go beyond yield, because up to ultimate it is a bonus. But majority of the time we will prefer below yield strength of the material. Then when you are trying to roll the sheet and make the rocket motors, there will be some mismatches. So the mismatch also will create a defect type thing, discontinuity stress, which increases the stress and reduce the load bearing capacity. So how best we are able to predict the stress concentration effect created by the mismatch? And the burst pressure is 15.2 megapascal, whereas the theoretical assessment is 14.6 megapascal, 4% lower than the estimation. The another one is 2-meter dia. Here, the properties which we have fed for the analysis may be closer to the reality, or just it is coinciding. It is really a surprise news. So 10.3 megapascal is the burst pressure, and we are able to get 10.3 in the calculations, estimations. Maybe, but we have to live with factor of safety. Otherwise, there will be some unexpected failures can take place. We have to pay huge penalty because of its failure. Now, when you talk about the fracture mechanics, there are two things. When you talk about stress intensity factor, earlier what we are discussing is for the applied load, stresses will be there, stresses will be compared with the strength of the material. The moment a damage is created in a body, then we need another thing called fracture toughness of the material, for which for the applied load in the presence of a crack, what is the stress intensity factor we have to calculate. So now all software packages are having capability of determining the stress intensity factor, so that for the applied load in the presence of a crack, whatever the stress intensity factor is coming, that should not exceed the fracture toughness of the material. So what is the safety factor? Fracture toughness of the material divided by the stress intensity factor will give us the safety factor. Crack growth phenomena is similar to the fatigue, but in fatigue, we are not introducing the crack, but after number of cycles, damage will be created and grow further and fade. Whereas in the presence of crack growth phenomena, you are artificially introducing a defect, and afterwards you are applying a cyclic loading and monitoring the crack growth. So there, change in the crack with respect to the number of cycles and what is the change in the stress intensity, these two variations will give the crack growth. So what happens in the absence of the cracks, the induced stress under internal pressure should not exceed the strength of the material. If it exceeds, it fails. Whereas in the presence of the crack, intensity of the stress should not exceed the fracture toughness of the material, otherwise it fails. So the factor of safety, one is strength divided by applied stress, the another one is fracture toughness divided by the applied stress intensity factor. So this is a simple example. When we are introducing a cutout like a circular hole for a simple tensile specimen, if the circular hole is not there, uniform stress distribution you can expect. The moment circular hole is there, whatever load you have applied for a wide plate, 3 times of that stress will be coming near the vicinity of the hole. If it is a elliptical hole, again, the small radius of the curvature, the stress will be there. If the elliptical hole where the minor axis is reduced to 0, it becomes a crack. so that the stress concentration will become infinity. So it is unable to take any load for infinite stress concentration, whereas in the presence of a crack, it is able to take the load. That way, the strength of material fails to give the correct factor of safety in the presence of crack-like defects. So there are three types of modes of failure. One is opening mode. You are applying perpendicular to the crack surface, the crack will try to open and it will grow and fail. Slide mode, shear typing, and tearing mode, third mode. Out of these things, the mode 1 is the toughness is low, it governs the design. The other things are still higher. If you design based on the mode 1, the structure, failure of the structure, other modes will be rare. So with that, the designers are adopting mode 1 fracture toughness. The cracks will not be a regular shape. They are irregular shape. These shapes of the cracks will be either surface crack or embedded crack, or you will be mapping as a semicircular or semi-elliptical cracks. So that for analysis it will be easy, and it has to cover the entire cross section of the zigzags variation of the cracks. So this way, the modeling can be done. Many standards are available. American Society for Testing Methods to determine the fracture toughness of the material, to determine the crack growth rate. So these standards, if you follow and generate the new material data, so that will be close to the realistic. But many failure assessments were also there developed, but none of them met the satisfactory results for all materials. One method may be working for one method. Another material you may have to adopt a new one, or you have to search for a suitable one. That is what from the beginning itself I said, experimentation on different materials. Theoretically, something will work well, for others it may not work well. We have to search for a suitable one. This is one of the relationship between the fracture toughness and the fracture strength. Through that, you can find for any geometry. You can find for any geometry, any location the crack is there. If you know the stress intensity factor, and if you supply the stress level, you will be in a position to detect, find the failure load of it. This is called failure assessment diagram. Depending upon the material properties, some of the curves, these properties I have changed one of the parameters 0 to 1. So the failure assessment diagram also accordingly it will be changing. The moment m is equal to 1, it is applicable for brittle type of materials. And cracks can be in a lab specimens. In a plate configuration, you can introduce center crack. In a shell or cylindrical vessels, you can introduce a surface crack or through crack and test it and verify the assessment, failure assessment with the measured data. So if you look into it, a lot of different diameters and width of the plate thickness, the crack dimensions were given, fracture strength is measured, and through analysis also. So what we see is below 5% error we are able to predict. That 5% you have to accommodate while fixing the factor of safety for the component. So this is another failure thing, whether the defect is surface crack, whether the defect is through crack, the failure assessment diagram is working well within the 5% error. So the another one is also indicating plus minus 10% of the variation for complete range of the predictions. So you have to select the factor of safety above 10%. These are the mining process, the composite pressure vessels were made. When you go for the upper stages, lightweight structures we have to do, and it should solve our purpose. So metallic means its weight will be there, so that the payload penalty will be there. So if you use the composite structures, what will be happening? The payload can be improved and it will do better job with high strength and all. But realization of the product which will satisfy our safety requirements is more important. Extensive studies have been made in ISRO, and now they are successful in realizing the composite through winding process, the composite pressure vessels, Kevlar. Now, composite strength and failure criteria. There are many criteria are available. One is maximum stress failure criteria. So among the components, maximum principal stress you find out and verify with the strength of the material. Otherwise, maximum strain, similar way, principal strains you can find out and compare this. Sci-Hill failure criteria, it involves all the components of the stresses, similar to in metallic case, von Mises yield criteria. It is widely used. Still, many criteria were being used which demand more strength properties in the directional properties. So, if you are assuming any one of the strength property because of the lack of the data, we may have to pay penalty. So, what is happening? Software will give you, depending upon the data which is available, on that it will assess the failure. Then when you talk about the flaw sizes, there are many types of defects: delamination, debonding, the fiber breaking, many such type of things. Each situation you have to apply different theory, different material properties to estimate its life, and finally you have to give the clearance for all possible type of defects existing in your body. I will recommend this product for further use in service. So we have to select and simplify as simple as possible. Otherwise, it is a time-consuming process, and some of the methods when you are using unnecessarily, it will alert us. But finally, we will overlook that one next time. We may have to pay penalty. So in general, whatever methods were there, they predict well for all composites materials, but what is happening? A simplest, easy to use in the design and adopt. So we have developed the inherent flaw model, modified one, and average stress criteria, and point stress criteria, and verified a large fracture data on several composite materials, and finally recommended. So, what is the meaning of the inherent flaw model? Means any cutout is there, there is a chance of stress rise. So that inherent flaw, one crack will be generated from there only, it will propagate and fail. If you are able to understand that zone, then your prediction will be close to the exact. So what will be happening? It demands test data. From the test data, you try to superimpose and get what is the inherent flaw size, apply that flaw size to other components and get the thing. Similarly, point stress. When peak stresses are coming near the discontinuity and afterwards it is dying down, for the applied load, where it is reaching to the allowable stress level, that distance, that point only, the point stress criteria. The moment at that point only you start comparing for a different stress level, you can find out as the point is moving, the load bearing capacity also will be reduced. This is average stress criteria. When the stress is varying in a non-linear fashion, why not we take the average of that and see the average stress whether it is exceeding the strength of the material or not. So all the three fellows are equally good when we examine for different composite materials. So you can select any one of them and use it. So these are all how we are relating the fracture strength to the crack size with the fictitious or a characteristic length ahead of the crack. So what all the test, what we have observed is the inherent flaw or characteristic length is not a material constant. It increases as the notch size is increasing. Then the strength will be decreasing with the crack size is increasing. What about the fracture toughness increases with the crack size? So what will be happening? Two parameters. One is KQ infinity, another one is sigma n infinity. Means for wide plate, if you are trying to get it, for finite width plate, you can apply the correction factor and translate it. So that each and every time we need not do analysis, sophisticated analysis for all the geometries. So these are all the relations between KQ and KNC. So that KF and M you can determine at least a minimum of 3 tests. One is unnotched strength, another one is 2 different crack sizes. You find out the strength values. From there you can get the values so that these formulae you can use it for estimating the fracture strength of the materials. So when you look into it for a different hole diameters, what is the stress concentration factor? If you use stress concentration factor, how much reduction it will be there? Then what is the inherent flaw length? It clearly indicates that variation with respect to the strength, and the predictions are within 5%. Then when you are going for the impact, this impact loading, what will be happening indirectly relevant to the energy. So majority of the people, they are directly relating the strength and the impact energy. Instead of that, if you non-dimensionalize them and use it properly, it will listen to us. So not just curve fitting means that may be valid only as long as your parameters are within that. So here, that impact loading, when you see what is happening, there is a relation, that equation 22, there is a relation between the strength as well as the energy. So as you know, the kinetic energy is half mv square, velocity, mass. So one side, that one is balancing. Then afterwards, one of the parameters you have to determine from the parameters, whatever test you have done. So lot of test has been done for different velocities. What is the energy and what is the, for the defect, what is the strength? Then when you put this data in that equation, it is following the path. So this is what the residual strength of some laminates after impact. So like this, different materials, different tests have been done and proved that the established theory is working well for the material. Similar line, we have to develop those parameters for different materials automatically. Since this is in non-dimensionalized form, it has to tell you. So majority of the things, the test data is following the path of the theoretical curve. So this is another data where repeated tests, some variation is there. That variation could be due to exactly the dimensions may not be crack and the depth may not be exactly. Slight variation will be there. It resulted in notch tensile strength in different way. So some little discrepancy is seen when you see. However, within 15% error, we are able to get the solution for the impact load also. So what is happening from this is residual strength after impact, it may be completely penetrated. If it is completely penetrated means you can map that as a circular hole. If it is partially penetrated means it will be a part through type of defect. It had to be given special treatment. If you apply acoustic emission for the material, automatically whether it is partially or fully, it will be in a position to find out the residual strength of the body. Then the impact velocities, whenever we are talking, the introduction of notches or stress concentrations in composite laminate can cause reduction in the strength. So that is what we are saying. A envelope, a envelope was shown to you earlier in the previous slide. One side, the y-axis is strength ratio, the x-axis is energy ratio. Both are in non-dimensionalized values. So now, how to create a damage? One simple thing for composites is the moment you are drilling, automatically delamination will be coming at the edges. The delamination will be coming at the edges. Because of that, what will be happening, though you are drilling 5 mm hole, it will be showing 6 mm effect. So how that thing can be done? Here, the process parameters for drilling, feed rate, and this is the spindle speed and drill diameter. 3 parameters are there, and 3 levels we have fixed. Strictly speaking, we require 27 tests, 3 into 3 into 3. But when we apply Taguchi design of method, we require only 9 tests, and we can predict 27 test results. So that is the beauty of the Taguchi method. We adopted and found from the analysis of variance, the feed rate is showing the percentage of the contribution is around 94%. The spindle speed is 4%, drill diameter is showing 0.77. So when you talk about this, we are able to establish the empirical relation through that all 27 experimental data can be done. That equation 2 will show the experimental result. Then how to validate? So we have drilled the other test runs for different feed rates and spindle speed and drill diameter. We measured the delamination factor and compared with the estimate, they are tallying well. Other one is acoustic emission monitoring. In this acoustic emission monitoring, what interesting study is, without a defect, just a tensile specimen they have loaded till its failure, the AE counts, cumulative counts they have measured. Afterwards, they artificially drilled the hole and did the same exercise. Then what happened, as the hole diameter is increasing, at the time of failure, the acoustic emission counts happen to be the same. So near the failure, either the defect is there or cutout is there, without cutout, the AE cumulative counts remain constant. That has given a motivation to create the problem. So for different hole specimens, what is the applied stress and what is the strength value related to AE counts? We are able to fit that data in this curve and plotted the test data versus the theory. So everything is supported by the test data. Afterwards, what happened? We are able to predict. For example, I am applying a stress of 100 megapascal for no hole. So what is its life? Test is 173, whereas my equation is predicting 171.4. If you put the hole drill 10 mm diameter for 50 megapascal stress, the test data is failure stress data is 89.7, whereas the assessment 85.7. So what happens? The acoustic emission is indirectly helping us to assess the residual life of the composites. When you go for the bond strength, as you know, the edges of the bond will have the peak shear stresses and normal stresses. So the failure will initiate at the edges of the bond. Afterwards, it will break, separate. So that concept, the point stress criteria, whatever we have applied for the composite materials, the same thing we have applied for the bonded strength, we are able to estimate the life. We are able to estimate the life. The another one is by varying the bond length, we have measured the failure load. This different theories we have applied, finite element analysis, as well as the analytical solution and all. Whereas the point stress criteria, whatever we have done, it is closely matching with the test data. So the point stress criteria, it assumes a inherent flaw, a defect. At that point, what is the stress is coming accurately, it can measure, then you will be in a position to identify at what load it will be failing. Then metal-lined composite overwrapped pressure vessels, even now it is a hot cake. Some people will be metal-lined, they are using, without liner, linerless also they are trying. But whatever the gas or whatever you are storing in the pressure bottle, it should not leak. And at the same time, it should have high pressure so that the safety precautions will be more. So one particular type of carbon epoxy material we have taken and whose properties were given, and the liner we are taking as aluminum liner. These properties we have used because directional properties are changing, means transverse tensile strength, transverse compressive strength, they are entirely different. So when you are applying in a multi-axial stress state, all the direction of the things at a point can occur. So prediction of the failure will be involved. That's why there are many theories available. Even commercial software packages also available. So how best the solutions are, we made a comparative study with the comparison. Second one, using isotenside dome. The dome profile, it is not our choice. It is as for the differential equation we have to create by seeing the end openings as well as the diameter of the cylindrical portion. We will fix the dome shape. So by following that one, we are able to get this is the dome shape. So liner, aluminum liner we have created. Over that we have wound the filament. So this is the dome thickness variation, and the thickness also will be varying. Then up to inflection point, and afterwards beyond the inflection point, you have to see a design path. We have to develop the design path and do it. This analysis, we have used the finite element analysis and measured. You please see for each pressure level, what is the maximum stress criteria? Hoffman, Tsai and Hill, Tsai and Wu, and Hassan. When you look into it, the index, whenever index is crossing 1, it fails. So around 110, this fellow is crossing. 120, this fellow is crossing. So actual burst pressure is 125 megapascal to 126, but numerical simulation is varying close to 120 Psi and Wu criteria. Psi and Wu criteria is tallying close to that. And whatever they place and all those things it has predicted, it is close to that. So from this, what is happening? The properties of the material is correct. And the second one is one of the theory where we have utilized all the strength properties in all directions made us come to close to the reality. So these are all the from the publications I have prepared this presentation. So what is required is whatever material we are trying, better to acquire all the mechanical properties and the strength properties, and we should have good non-destructive testing methodology to see how good the health condition of the realized component, so that our assessments will be close to the reality. So this is what the different things. So now even non-destructively, we have to estimate the lifespan of the component. That is what the expert system people are trying to develop. Individual component to a certain extent is okay. When you assemble all the components, still we have to develop the necessary expertise, because where it will initiate, how the failure can grow, and all those things very difficult to assess unless it is supported by the experiment. So that is the reason the structural integrity analysis is very important for assessing the life of the component and to estimate the safety of the component prior to use in service. So this is what my presentation. These are the references where we have done the complete the presentation details are available. If any questions from the audience side, I am ready to answer.
Thank you, Professor, for your insightful and thought-provoking keynote address. The
Yeah.
knowledge and perspectives you have shared today will undoubtedly inspire new ideas and spark further discussions among all of us. We sincerely appreciate the time and dedications you have invested in making this section so enriching. Now, the section is open for the Q&A. I kindly request the audience to type their questions in the chat box so we can address them one by one. Let's make this an engaging and interactive section. Yes, sir. We have the first question from Gobika VK. The question is, challenges in predictive modeling and experimental techniques to improve the reliability of failure theories for diverse composite material.
They are asking. Madam, come again.
Okay, one.
Professor, actually the question is, what are the challenges in predictive modeling and experimental techniques to improve the reliability of failure theories for composite materials?
Yes. See, any new theory, we require experimental evidence. So, failure theory, when you talk about it, we have to compare the stress with the strength of the material. Composites being a multi-directional, the strength properties also will be changing in all the directions. We require the all directional properties have to be determined and select one of the thing. Even right now, worldwide composite failure theories, lot of theories they are publishing, they are giving the experimental data. If you have any other data, if theory is available, you please put it. So that with that knowledge, they are introducing in these commercial software packages also. So one is the stress evaluation, how accurate you are, your stresses, and the strength, how accurately you are measuring the strength of the properties in other direction. It matters.
So I think we have one more question. Professor, in fatigue loading or in cyclic loading, what is the role of acoustic emission monitoring? That is, how this can enhance the accuracy of damage evaluation and failure prediction in composites.
See, whenever we are doing the cyclic loading and all, in cyclic loading, we are not bothered the damage is created for each up and down loads. What will be happening is, well below the strength of the material, the fatigue cycle will be doing. How many number of cycles you will apply? That we have to collect the cycles, number of cycles under this spectrum, means minimum load to maximum load, what is the stress amplitude, what is the mean stress from there, what is the number of cycles it will be coming. Those things are important. Acoustic emission monitoring, slowly when you are applying a load, where the defect formation can be there, it will give alarm and it will identify the acoustic emission where it is. It is not only acoustic emission will solve all the problems. There are many non-destructive testings are available. We have to select. But in case of fatigue, the final failure, what is the number of cycles only will be recorded. There we will not apply. Otherwise, after each cycle, you have to see the health condition.
I think there are no more questions in the chat. Over to you, Nibi.
Once again, thank you so much, Dr. B. Negeshwara Rao. Your detailed response to all the questions are much appreciated. We also extend our heartfelt gratitude to all the participants for their active involvement and thought-provoking questions. Thank you once again and have a great day ahead. Next is the validatory section, and which will begin shortly at 4 p.m. Thank you.
Thank you very much, Professor,
Okay, thank
for
you, ma'am.
joining and sharing your wonderful presentation and your thoughts. Thank you. Thank you very much.
Thank you.
So, dear participants, we are come to the end of the final keynote of our ICRACM